Heating and air conditioning operation. This training tape will summarize the operating principles of air conditioning and heating systems. By understanding the underlying theory or physics of refrigeration and heating systems, you'll be more prepared to diagnose and repair these systems when they fail to work properly. The video will use computer animation mixed with live-action footage of actual components to make your learning more fun and efficient. The other two videos in this set will demonstrate troubleshooting and service techniques for automotive air conditioning and heating systems. Since a large percentage of cars now come equipped with air conditioning, it is important for you to grasp how a properly operating system functions and how it is repaired. This information will make you a more valuable, productive automotive technician. Good luck in your further study of automotive technology. The basic parts of an automotive air conditioning system include a condenser which mounts at the front of the car to remove heat, a compressor that bolts to the engine and pumps refrigerant to other parts of the system, an accumulator that mounts before the compressor to collect moisture and liquid refrigerant, an evaporator mounted on the firewall for cooling the passenger compartment, a heater core also on the firewall for warming the passenger compartment. To fully understand these parts, you must first comprehend a few simple laws of physics. There are three states of matter, with water as a good example. There is a liquid state at room temperature, vapor or gas state when the water is heated above its boiling point of 212 degrees Fahrenheit, and a solid state when water is cooled below 32 degrees Fahrenheit. When a gas condenses into a liquid, heat is released to surrounding objects. However, when the liquid vaporizes into a gas, heat is absorbed. Since cold is really the absence of heat, this is important to refrigeration because the refrigerant is forced to change from a liquid into a gas, then back from a gas to a liquid. This makes the system absorb heat during vaporization to produce cooling, then release heat during condensation. Conduction, convection, and radiation are the three methods of heat transfer. Conduction is heat transfer when objects are touching. Convection is heat transfer through the air surrounding the objects. The objects are not touching, and the air provides a medium for heat transfer. Radiation is another form of heat transfer caused by infrared rays, as from arc welding or the sun. The rays transfer heat to the other objects without the presence of air. If you enclose a medium, air or a refrigerant for example, in a cylinder and compress it with a piston, the pressure and temperature gauges would both go up. This would prove that when you pressurize the medium, its temperature increases. When you reduce pressure on a medium, air or refrigerant, its temperature decreases. These basic laws of physics allow the operation of an air conditioning system. As this diagram shows, Changes in pressure and state allow for a cooling process to take place. The refrigerant is compressed and heated. Heat is released. Then, as the refrigerant vaporizes, heat is absorbed to produce a cooling effect. This animation demonstrates the basic refrigeration cycle. On the right, a compressor pumps refrigerant in a high-pressure vapor state into the condenser. The condenser allows heat to transfer out of the refrigerant, causing the gas to condense into a liquid. The high-pressure liquid then flows to the Orifice Tube restriction on the left. When the high-pressure liquid squirts through the small opening, its pressure and temperature drop. In the evaporator, shown at the top, the refrigerant vaporizes and absorbs heat to produce a cooling effect. Low-pressure vapor with some liquid then flows into the accumulator at upper right. It stores the liquid but passes the vapor. Low-pressure vapor is then pulled into the compressor and the cycle is repeated. For service and repair purposes, you must understand which components are in the high and low sides of an air conditioning system. Also called the discharge side, the high side parts include everything between the output of the compressor and the inlet of the orifice tube. The low or suction side includes the parts between the outlet of the orifice tube and the inlet of the compressor. As you will learn, the exact parts in each side of the system can vary in design. Mentioned briefly, an air conditioning compressor is a refrigerant pump. It often bolts on one side of the engine near the front. High-pressure refrigerant lines feed refrigerant, or R12, in and out of the compressor. The compressor is normally driven by a V or ribbed belt running off the engine crankshaft pulley. Engine power is transferred to the compressor by the drive belt. This cutaway shows the basic action of an older V-twin type compressor. The pistons slide up and down in cylinders to produce a pumping action. The crankshaft is driven by the compressor pulley and forces the rods and pistons to move. Since the compressor crankshaft is pressurized, it must be tightly sealed to prevent refrigerant loss. Here you can see a compressor shaft seal. It prevents oil and refrigerant from leaking out of the clearance between the spinning crankshaft and the compressor housing. Reed valves are one-way valves that make the refrigerant flow through the compressor and system in only one direction. This is an older style reed valve. Note how it has a thin steel flexible membrane or valve. The plate will flex open to pass vapor in one direction, but flex closed and seal off the opening in the other direction. Here is a newer style reed valve, but it works the same way. Study the fundamental action of reed valves. One reed valve opens on the piston downstroke while the other closes. Then on the piston upstroke, the action is reversed. This causes flow through the compressor and lines in only one direction. Some compressors use an oil pump. A pump is used when the compressor is equipped with a sump or storage area for oil. The oil pump is rotated by the end of the engine crankshaft. This causes oil to be forced through the internal passages of the compressor to lubricate moving parts more efficiently. A service valve or valves may be provided at the top of the compressor. The cylinder head bolts to the top of the compressor body or case. Reed valves mount under the cylinder head, above the cylinders and pistons. The pistons slide up and down in the cylinders to form pressure. The rods link the crankshaft with the pistons. The crankshaft converts a rotating motion into an up and down motion to power the pistons. Mentioned earlier, a sump is sometimes provided to store an extra supply of refrigerant oil. This is a crankshaft piston assembly out of a 4-cylinder radial compressor. Note that its construction is quite different. The piston houses a suction reed valve, and a conventional connecting rod is not used. 4 pistons are mounted on 2 yokes. The yokes react to motion from a slider block that rides on the crankshaft eccentric. As the crankshaft turns, the eccentric acts on the slider blocks and yokes. The cylinder block provides bores for the pistons and also houses the discharge reed valves. A large metal ring fits around the block and seals against large O-rings. This is a lightweight, compact compressor design. Here you can see the basic motion inside a radial compressor. The pistons move in and out around a central crankshaft axis. This is a 6-cylinder axial compressor. Note that it has a pressure release valve on the rear head. A fitting is also provided for a sensor. This type has a sump and a drain plug for replacing or checking refrigerant oil. This animation shows the basic action of a 6-cylinder axial compressor. A wobble plate turns with the compressor shaft to move the piston sets in a back and forth motion. With 6 cylinders, this larger heavy-duty compressor design can still be found. Here is a more modern axial 5-cylinder compressor. Its wobble plate reacts on the 5 pistons as shown. This is a slightly smaller compressor design. Some wobble plate type compressors are variable displacement. The wobble plate can be moved to change the effective stroke of the pistons. This provides for more efficient operation, reducing fuel consumption and power loss. Another compressor design is the rotary compressor. It uses sliding vanes in an offset cylinder to produce a pumping action. An electromagnetic clutch is used to engage and disengage the compressor crankshaft to and from the compressor pulleys. Here you can see the terminals leading to the compressor coils. The compressor clutch consists of an electric coil, a pulley, and a front clutch plate. When current is fed to the compressor coil, the clutch is engaged and the compressor begins to run. When current is shut off to the coil, the compressor disengages. This animation demonstrates what is happening inside the compressor clutch. When no current is fed to the electromagnetic coil, the clutch pulley freewheels. When the coil is energized and the electromagnetic field pulls the plate into the pulley, the two turn together and the compressor kicks in. This cutaway shows the magnetic coil inside a compressor clutch. The clutch plate reacts to the magnetic field caused by the coil. The belt pulley is powered by the crankshaft pulley through a V or ribbed belt. The compressor shaft transfers power from the pulley and plate into the internal components of the compressor. The clutch assembly rides on a set of ball bearings. Since the condenser must remove heat from the refrigerant, it is normally mounted in front of the car's radiator so that cool air can pass through the grill and condenser fins. The evaporator is mounted under the car dash so that it can absorb heat and cool the air entering the passenger compartment. We've cut this evaporator in half to show its construction. Note that it is simply a series of hollow passages surrounded by metal fins. The fins allow a large quantity of heat to be pulled out of the air flowing through the evaporator. The evaporator is often made of aluminum for rapid heat transfer and to save weight. Metal lines feed refrigerant into and out of the evaporator. Note the accumulator on this evaporator. This is a close-up of a condenser and cooling system radiator cutaway. Their construction is similar. All the tubes are surrounded by cooling fins. The action of the engine fan pulls outside air through the condenser and then through the radiator. This removes heat from the refrigerant and from the engine coolant. The heat removal in the condenser makes the high-pressure refrigerant vapor change into a high-pressure liquid. Refrigerant hoses and lines carry R12 to each component in the system. They are very high-pressure hoses and tubes designed to withstand compressor vibration, extreme temperature changes, and high pressure values. The air conditioning hoses and lines carry refrigerant from the compressor to the condenser, to the evaporator, and then back to the compressor. Clamps or straps are often used on long sections of line to prevent excess vibration and damage. Refrigerant lines and hoses are normally designed to withstand up to 1,500 pounds of pressure, even though normal operating pressure averages about 200 pounds. Note that a sight glass is provided in this refrigerant line. It allows you to check general state of charge in the system. Various types of fittings are used on the refrigerant lines and hoses. The top fitting has a metal tube with barbs that lock onto and seal on the hose. A hose clamp secures the hose to the barbed fitting. Only special high-pressure neoprene hose can be used in a refrigeration or air conditioning system. The middle fitting is a factory design that uses an O-ring to produce a seal. The fitting flange clamps against the O-ring when the fitting nut is tightened. This fitting has a factory crimped connection to the hose. The metal tubing is crushed down around the hose to produce a leak-proof joint. Flared tube fittings are sometimes used. When the fitting nut is tightened, the flared tube end seals against the mating surface on the other component. Here you can see typical O-ring seals used on the back of the compressor. The seals fit into machined grooves in the compressor housing. When the refrigerant lines are bolted into place, they slightly compress and seal against the O-rings. An accumulator must trap liquid refrigerant before it can enter and damage the compressor. It must also trap and store moisture that could cause system corrosion and damage. An Orifice Tube type air conditioning system uses an accumulator in the low side of the system. The accumulator is located at the outlet of the evaporator, usually on or near the car's firewall. Any liquid refrigerant settles to the bottom of the housing. The vaporized refrigerant floats out the top and is pulled back into the compressor inlet. Liquid R12 vaporizes as it warms inside the accumulator. Note the desiccant bag, which absorbs moisture. A service fitting is often provided on the accumulator for connecting your low pressure gauge for testing system operation. The red line shows the high pressure inlet to the evaporator right before the orifice tube. This blue line shows the low pressure outlet from the accumulator. This is an expansion valve type air conditioning system. Note how it differs from the orifice tube system discussed previously. This type air conditioning system uses a receiver dryer instead of an accumulator to prevent vapor from entering the expansion valves. It also removes moisture. It is located in the system high side right after the condenser. Here's a cutaway of a typical receiver dryer. The unit contains a desiccant or drying agent of silicon gel to remove water from the refrigerant. This prevents damaging system corrosion. The desiccant is normally enclosed in a bag to keep small beads from entering the system line. A sight glass may be located on the top of the unit to show the state of charge or how much R12 is in the system. The Orifice Tube or clutch cycling air conditioning system is the most common type used today. The Orifice Tube normally installs in the line feeding into the evaporator. Small dimples crushed into the metal line hold it in place. It has a filtering screen to keep debris from clogging the small orifice or metering hole. An O-ring seals the gap between the outside of the orifice tube and the inside of the metal line. An expansion valve is a temperature-sensitive flow control valve. It controls refrigerant flow and the evaporator temperature. A sensing bulb reacts to the temperature changes at the evaporator to open and close the expansion valve. This valve has an extra line which allows it to be pressure balanced. When the sensing bulb and evaporator are warm, the expansion valve is open to increase R12 flow and cooling action. When the evaporator and sensing bulb are cold enough, the expansion valve closes to block R12 flow. This controls the temperature of the evaporator. This is a VIR, or valves in the receiver assembly. It combines numerous components in one device. It contains a service valve fitting, 3 line fittings, a sight glass, the expansion valve, pilot-operated absolute valve, and a receiver dryer, all in one assembly. This is the expansion valve. This is a POA valve, which senses evaporator pressure to help control system temperatures. A car's heater normally uses engine coolant to warm the passenger compartment in cold weather. Hot engine coolant circulates through the heater core. Heater hoses connect the heater core with fittings on the engine. The engine radiator is similar in construction to the heater core. The water pump forces coolant through the radiator hoses, through the radiator, through the heater hoses, and through the heater core. Here is a heater core removed from the car. Two fittings are provided for the heater hoses. It is simply a series of tubes surrounded by fins. Air flowing through the core carries warm air to the passengers. This is a heater control valve used in some systems. It can open or close to control the flow of hot coolant through the heater core. It is vacuum operated. The vacuum diaphragm opens or closes the valve by operating off the supply vacuum provided by the dash control panel. Here you can see how the heater hoses fasten to the heater core. The blower forces air to either the heater core or the evaporator, or both. The heater core and evaporator are enclosed in a plastic housing. The housing bolts to the underside of the dashboard or to the firewall. Here is one of the flaps that controls airflow to the housing and ductwork. The flaps can be opened and closed by cables, by vacuum motors, or by servo motors. This is a typical duct system. The air doors on this unit are operated by cables attached to the control panel. The control cables are simply metal wires enclosed in a flexible cable housing. Sliding the lever from the dash control moves the cables to open or close the flaps. The control panel also has a blower switch which electrically energizes the blower to force air through the system. Here's a control panel removed from the dash. This is your temperature selector lever, which operates a cable going to the flap. The buttons select the mode of operation. A switch is provided for the fan. The rear of the control panel shows electrical terminals for the blower motor, the compressor clutch coil, and vacuum connections which use rubber hoses to route pressure to the vacuum diaphragms that operate the air doors. Note how when you move the temperature selector, it moves a lever which would be connected to a control cable. Various sensors are used in modern air conditioning systems. This is a pressure sensor used in a clutch cycling or Orifice Tube system. The pressure switch can turn the compressor clutch on and off to control system operation. The ignition switch normally feeds power into relays. The relays then feed current to other components. The engine radiator fan is controlled by a coolant temperature switch. If used, the condenser fan is turned on by the compressor clutch circuit. The blower motor switch and AC switch provide driver control of the system. Both thermostatic and pressure sensing devices are used to provide information to the ECU. The ECU can then energize the compressor clutch. The two other videos in this set discuss heating and air conditioning systems in more detail.